Okay. Let's grab that one and this one. And swap displays. Okay, how does that look for everyone?
Looks good.
And you can hear me. Terrific. All right, I'll try to be quick, but I'm very excited to be here and share with you where we are with EMIT and the release of the first 5,000 image cubes. EMIT stands for the Earth Surface Mineral Dust Source Investigation, and we'll talk a little bit about what that means, but also the measurements we're making, we clearly view enable additional science applications and, in fact, excitingly, some greenhouse gas work also. So let's proceed. So EMIT was proposed to investigate a gap in our knowledge about the mineral composition of the Earth's arid land regions. There is a dust cycle in our Earth system where with high winds, dust is blown into the atmosphere and interacts directly with the atmosphere, with the sun, absorbing or scattering, forming clouds. When it's deposited, it can fertilize aquatic ecosystem, terrestrial ecosystem. When it lands on snow, it melts. And when it interacts with us in our cities and environments, it can be visibility and, in fact, a toxic hazard. So it's an element, and right now we don't have a really good knowledge of what the composition of the regions where this dust originates. So that's the focus of EMIT. And so these are the regions that we've identified as a science team that we needed measurements to characterize the source region. So that's a large portion of the Earth. It's largely arid lands, and it falls below the orbit of the International Space Station, which is the platform that we're mounted on. But I will say, in an extended mission, we would have access to the other areas that fall below the space station. But right now, the data sets you're seeing are collected aligned to a very large degree with this target mask and some ancillary calibration and validation data sets. The approach we're using to determine the composition of these arid land regions is imaging spectroscopy. It's something I've been involved with for more than 30 years. In fact, at JPL, we built the first imaging spectrometer. Sorry, that was the phone coming in. Apologies. And in any case, so the concept of an imaging spectrometer is that we look down at the surface of the Earth in this case and collect light in a swath. So that's the cross track, the left-right direction. In the case of EMIT, that swath is about 80 or 90 kilometers. It's quite wide. Take that light into a telescope, into a spectrometer, put the samples onto different columns of the detector array, and record those data and deliver them for use for calibration and then material mapping. We built the EMIT imaging spectrometer starting in October of 2018 in 41 months, and that was with COVID, which is fairly quick for hardware of this sophistication. And delivered it in March of 2022. And there are some pictures of the optical design on the left, the hardware instantiation, a CAD model, and on the lower right, that's a picture of the EMIT instrument in the laboratory at JPL before we shipped it for a launch. We had a very good day in July on the 14th, also Bastille Day, with the launch of EMIT to the space station. It docked on the 16th. It was transferred by the robotic arm to its location. You can see it there sitting in the lower right on the 24th and turned on and began to deliver measurements on the 28th of July. These are the first light images. So these are the first spectral image cubes we collected from EMIT on the 28th, and they met and exceeded our expectations. We're seeing all the spectral signatures of the Earth system. So remember, EMIT measures photons that originate from the sun, interact with the Earth's atmosphere, interact with the surface, back up to the atmosphere, and we measure them. So we get the full Earth system signal. There's lots of exciting potential with the fact that we've done that. We just do atmospheric correction, and you'll hear more about that as we get to our surface products, but we can also study the atmosphere. This is some recent data from EMIT collected in January 7th of 2023, where we collected an image cube near Cape Town, South Africa. You can see in the upper middle the radiance that we measured, and then in the upper right, we've now done atmosphere correction. Those are the reflectance spectra that preserve the spectral signatures related to those minerals, which is the mineral composition. That's the core EMIT objective. And again, our spectral range is quite broad, from the visible 400 nanometers well out into the shortwave infrared to that 2500 nanometer region. So we capture fingerprints of lots of Earth system materials. And then below, from those mineral spectra, we can map the mineral composition. And these are the key minerals that EMIT needs to measure to achieve its science objectives. So where we are right now, I pulled this down this morning. I think this is what you're seeing is the coverage we've collected so far from our dust mask. The blue areas are early collections, and then the yellow areas, or yellow-orange, are the more recent collections, and then the green are actually the planned collections in the next 2 weeks. So EMIT is measuring spectra right now, and we collect data based on the sun elevation, and right now we're collecting quite a bit of data in the southern hemisphere, but we'll shift back up to the northern hemisphere as the illumination conditions improve. And then I've just put some cubes, image cubes around the edge to show the types of data, diverse data we've collected. So while we focus on the airland regions, we also get regions when we're near the airland regions of the coasts. We get snow-covered mountains on occasion because they're often right next to arid land regions. So there's quite a diversity in here, even though our prime focus is arid land regions. Where we are with EMIT, we're right on track to achieve our science objectives, which is our commitment to NASA, which is to constrain the sign and magnitude of dust-related radiative forcing and predict how dust sources might grow, increase, or decrease in the future. So you can see the steps. We understand dust leaves the surface. We have a target mass. We have the spectroscopy. We have an instrument, or we're collecting the data, producing the product, and we're going to use advanced Earth system models to address those objectives. So that's where we are with EMIT. And I wanted to leave you with that before I just give a little bit more about maybe why some of you are here. There's considerable added value from these measurements that we're making. And again, they span geology, resources, biodiversity, agriculture, fire fuels, hazards, surface plastics, snow and ice at mid-latitudes, algal blooms, methane and carbon dioxide. So we're aware of these. Their signatures are present in that spectral range that EMIT measures. So they may be areas that you will have different interests in using our data set. So I'll say a little bit more again, just highlighting, we've had the very nice result that we're very good at detecting methane and carbon dioxide super emitters, and these are some examples, and that'll be one of the applications that EMIT will be used for beyond its science objectives. So those are plumes, giant plumes of methane and carbon dioxide measured by EMIT early on in its observations. But I want to indicate also there's considerable work to be done with terrestrial ecosystems. For aquatic ecosystems, where we're near the edges of coasts, we've got coral reefs, we've got other things in there because in many areas those are adjacent to arid lands. Geology, of course, and even snow and ice hydrology, where we have mountains, snow-covered mountains. Reminding you, this is the current target mass is the red area. We have, in an extended mission, we will have access to all areas below the International Space Station. And again, there are a whole host of different science and applications that can be pursued with the EMIT spectroscopy, geology, ecosystems, the atmosphere, aquatic hazards, and snow and ice hydrology. And there's very low risk in pursuing this because, again, we have been flying airborne imaging spectrometers now for a number of decades. And so I just wanted to highlight here some examples that are in the literature where we've used airborne spectrometers to look at terrestrial ecology, aquatic hydrology, and geology questions, along with the spectral signatures that we use to address those advanced questions. So there's lots of evidence that this works very well, and the EMIT data set will support the expansion of these examples globally. And I've done the same thing for a set of applications: biodiversity, harmful algal blooms, mineral resources, water resources with melting snow, hazards, and fire, all of which EMIT measurements can contribute in the science and in the applications research area. So that's what I wanted to give you as a quick introduction. You'll hear so much more from the amazing EMIT team as we go forward. So thank you very much for your time, and I'll hand it back to you, Dana.
Great. Thank you so much, Rob. So now I think we're going to head over to David Thompson, who's going to continue our introduction into EMIT data.
Great, thank you, Dana. It's great to see the interest, all the attendance here today, people interested in EMIT data products. So this talk is going to be about sort of an introduction to the radiance and reflectance products that we've been delivering to the archive. And I don't want to presume any background in spectroscopic analysis. I see already from the participants list that there's some real veterans who might find this a little bit pedantic, but bear with me. I'm going to start with the basics of what the radiance and reflectance measurements mean, just to give you an intuition for these physical quantities that we're measuring. And this is important because spectroscopy differs from many other kinds of remote sensing in which the values themselves may not be as physically meaningful. It's more the image that matters. Here, we really are doing spectroscopy, fitting physics-based models. And so the units of measurement, the counts of the photons really do matter for our purposes. And so I want to give you a more in-depth explanation of what these reflectance and radiance quantities mean, so you can be a better, more informed user when you go to take advantage of the EMIT data products. Okay, so the EMIT data analysis pipeline takes several steps, and you'll eventually find all of these in the digital archive, but we're going to focus today on the early stages. That is the initial calibration step, in which raw instrument data is turned into a radiance measurement at sensor. Radiance here simply meaning a measurement of the incident illumination at the sensor at the top of the atmosphere, looking down from the ISS at the Earth, measuring the intensity of illumination in every pixel. And of course, this is a spectrally defined product. And this goes through an atmospheric correction step to infer the surface reflectance. Broadly speaking, that's the fraction of incident illumination at the surface that's reflected back in the direction of the sensor. And that's the level 2A product. And you'll be able to find this in the archive too. And I think for most of you who are interested in Earth surface processes, these surface reflectance products are really the product that you're going to want to use. But it's important to know how you got there. And some other folks may want the radiance products too, either because they want to do atmospheric studies or because they want to apply their own atmospheric correction. And then the EMIT science data pipeline from there takes the surface reflectance and interprets those reflectance spectra to infer mineralogical maps of the surface, the mineralogy at every pixel. And then aggregates those into grid squares that are eventually input into Earth system models to answer the fundamental Earth system level questions that the EMIT mission was designed to address. That is the nature of mineral dust radiative forcing in the Earth system. And we get there, of course, by looking at the mineralogy of the surface. These last three steps are important for EMIT, but again, for the broader user community may not be as important. So I'm really going to focus on these first few steps. It's also important to note that we have uncertainties for all of these products. In the radiance, this takes the form of a recipe that lets you calculate what the signal to noise will be for any given radiance spectrum. And in the surface reflectance products, we actually distribute uncertainties explicitly for every one of these spectral measurements that we make. So there's essentially a second file that contains the uncertainties that you can download and make use of. So Rob already talked about this, but EMIT is an imaging spectrometer, and it measures data cubes. So a three-dimensional object. All of these reflectance and radiance images are three-dimensional data cubes where we get a full spectrum of information at every pixel within the scene. And this happens by taking a push broom sensor, that is a linear field of view that's sort of pushed along the ground as the ISS orbits. And that light enters a telescope, is imaged onto a slit, dispersed off a grating, and then cast onto a detector array that sorts it by wavelength to create these beautiful spectra. And so we get a full spectrum at every point in the scene. But of course, since we're measuring light intensity, what we get is a measurement of light intensity, and that's our radiance spectrum. So what is a radiance spectrum? Well, it's microwatts, of course. So we're measuring energy, the photon's energy, and it's a quantity that's per nanometer. So every channel is measured independently, per steradian solid angle, per centimeter squared, unit area on the ground. So this radiant spectrum contains information about all the processes that have happened to those photons in their transit from the sun to the ground to the sensor. And you can see the fingerprints of those processes embedded in this radiant spectrum. To begin with, you'll notice that there are these divots here in the near infrared. These are water vapor absorption features from water vapor in the atmosphere that absorb some of the illumination, preferentially in certain wavelengths, following their molecular structure. This feature right here is the oxygen A band. This is molecular oxygen in the atmosphere. You'll notice as well that there's sort of a broad tilt where the shorter wavelengths of the spectrum have more energy than the longer wavelengths. And this is largely due to the illumination of the sun itself. So the sun puts out more energy in these shorter wavelengths, and that imparts sort of the broad feature that we see here, the broad shape of this radiance spectrum when it reaches the sensor. There's another feature to this spectrum, which is not of the atmosphere nor of the sun, but of the surface. And so some of you who are expert spectroscopists may have already recognized this feature here at 690 nanometers, which is the absorption of chlorophyll, which leaves extra photons here in the green at 550 nanometers. This is what makes trees look green to our eyes. And indeed, this is the radiant spectrum measured over some vegetation. So we see features of the ground, the sun, and the atmosphere all combined in this radiant spectrum. I've noted here as well the visible wavelengths that our eyes see, blue, green, and red, just so you have an idea of where those lie in the radiant spectrum as well. So this is the fundamental emit measurement that it makes at every location within the scene. A couple of things to note about this. First of all, it's based on a calibration that we conducted over the course of the instrument operations and checkout. This has been validated against ground targets that have been measured in situ. So we have validation and traceability of this radiant spectrum. Second is that it changes. It's a function of the observation geometry. So if the sun's in a different position in the sky, if it's low on the horizon, we'll have less illumination at the sensor, and you'll see the magnitude of this radiant spectrum shrink. So it's observer dependent. And it's also dependent on the gases in the atmosphere at any one given time. So if there's more water vapor in the atmosphere, if we're looking at a tropical target with a very wet atmosphere, these water vapor absorption features will be deeper. And this is why we'll eventually graduate to a different product, the reflectance product, which is an intrinsic property of the surface that doesn't change with atmospheric conditions. Okay, so let's dive into this radiance product first. This is the EMIT radiance file name that you see up top, and I've decomposed it for you so you can understand all the parts. The timestamp is fundamental. That's a unique identifier for this particular image, and that's on the left in blue. Also, the other blue over here, which you might want to pay attention to, is the product level, which designates L1b radiance for this particular cube that I'm going to show you. The others have to do with orbit and scene numbers and also the build version of the software. But fundamentally, I think we use timestamps more often than not to designate the data cube that we're interested in. So let me quickly jump out of this presentation and I'll launch a quick demo. This is with software called Wiser that's available at Caltech. It's a freely available software for viewing EMIT or other data cubes. It's very similar to Envy for those of you who are familiar with that software product. But since this is free and anybody who wants can download it, I'm using this for example. So here is an EMIT data cube that I've loaded up in this software, and you can see I can navigate around this image to all the different parts, and you're already seeing just the fantastic detail that we have in this 1200 pixel wide cross-track sensor. Just really fantastic detail on the surface. This is an image of the Andes, I believe, between Argentina and Chile. I've done a little bit of a visual contrast stretch here to bring out all the variety and different color of all these rock surfaces. If you were to be down there on the surface, you'd probably just see a bunch of brown rocks, but even in the visible, EMIT is capable of making very subtle distinctions between the radiance at these different locations. And up here in the upper right, you can see the radiance spectrum for the location in the image that I'm looking at. So if I click on different locations in the image, you'll see that radiance jump around. So indeed, for every pixel in the scene, we have a full spectrum of radiance data. And there are, of course, mineralogical differences, surface composition differences that are manifest in this radiant spectrum, but they're kind of difficult to see by eye because of all those overlaying atmospheric features and the nature of the solar irradiance, all those other properties that I showed you before. Oh, I see Aaron has put a link in the chat for the Wiser software. Thank you very much. Appreciate that. All right, so let's see. Let's pan around here and see if I can find some uniquely different materials. Here's a pool of water. So if I click on that pool of water, you'll note that we do see a pretty fundamental change in the radiance. All of the infrared photons have pretty much disappeared. It's because water is really an excellent absorber of photons in the infrared, but it reflects pretty well in the blue, so a lot of our blue photons come back to us. And this is, of course, why large bodies of water seem blue to our eyes. So we're already seeing some compositional differences, but they're subtle in the radiance representation. And we really want something more observer invariant than radiance to work with. So let's talk about surface reflectance, which is the next step in our journey. The EMIT surface reflectance product. So I mentioned before that radiance is related to everything that's happened in the photons as they've traversed from the sun to the ground of the sensor. There's some scattering off of atmospheric particles. There's absorption by atmospheric particles and gases. And there's also a population of photons that's reflected off the surface and comes back to the instrument. So you can imagine taking the ratio of all the incident photons to all of the reflected photons. And if you were to plot that as a spectrum, you get something like this. So this is the reflectance spectrum of that same tree that we saw appear in the radiance spectrum, but all of the atmospheric features are now gone because we're looking just at the effects on the surface. We're removing all of the features related to atmospheric and solar properties. So we see the red edge due to chlorophyll absorption is still here, but we see some new features related to liquid water absorption in plant tissues up here in the near infrared. We also see structural features due to woody plant tissues and other non-photosynthetic plant tissues. Those are evident in the shortwave. And we also see subtle variations sometimes in reflectance spectra of trees, minor bends and divots and wiggles in these spectra that actually capture information about canopy structure or even sometimes species. So there's a lot more information that we can glean from these reflectance spectra. And if we were to measure that same location under similar illumination, regardless of what the atmospheric conditions happen to be at the time, we should get the same reflectance spectrum, which makes this a much better property to use for mapping properties Earth surface properties globally. So here's an example of the reflectance spectrum. It's a unitless quantity, again, that represents, roughly speaking, the fraction of incident illumination that's reflected back at the sensor. Now, the important thing to recognize about EMIT reflectance spectra in particular is that it's defined as a directional reflectance measurement. So we are taking all of the illumination that's incident on the surface patch, including the direct beam from the sun, and also the diffuse illumination from the blue sky onto that surface. But we're only measuring the reflected photons in the direction of the ISS, wherever the ISS happens to be looking. So it's a directional measurement. And this means that we are sort of having to infer what's happening in all the other directions. There can be surfaces that reflect preferentially in one direction or the next, like a glossy surface can reflect strongly in one direction and less so in others. You can see surface glint off of ocean waves and things like that. So all of these are directional reflectance properties, but with EMIT, we aren't taking that into account. We're just saying that whatever illumination we happen to measure in our look direction, we're going to call that the surface reflectance. There could be other things happening in other directions. So just bear that in mind as you interpret the reflectance spectra. Reflectance is defined as if the surface were Lambertian, an isotropic reflector, but based on the measurement from one direction only. And this is typically how imaging spectroscopy works, but it has some interesting implications for the interpretation of these reflectance spectra. So now let's do a quick knowledge check based on everything that I've said up to this point. Why don't you put your answer in the chat? What is the possible range of values that EMIT radiances might take on? What is the possible range of values that you could see in EMIT products? So just put your answer in the chat. Give me a numerical range, high and low. I see one answer. Any others? Any other bold, courageous individuals willing to guess what the numerical range of legal radiances might be? Okay, I see some answers starting to come in. Okay, so I'm seeing values starting at 0 up to large values, and that's almost right. So radiances are measurements of energy, right? So you could imagine processes at the ground, like maybe flaring oil stacks or something that could add radiance beyond the natural radiance of the sun. So there's actually no upper bound on what the radiances are that you might measure from EMIT. In theory, you're probably going to measure radiance that's less than what the sun would provide. But in you know, in theory, you could measure anything. You could also, in theory, measure values less than 0. And that's because EMIT is a noisy sensor, right? There's some natural noise that goes on in any physical measurement process. So if you see a value that's slightly lower than 0, that's not wrong. That just means that there's some noise in that measurement of the 0 points. And we don't want to truncate that because we want our 0 spectra to average out to be 0 in the long run. So that was a design decision that we made in the Radiance product. Okay, so what about the possible range of values for EMIT reflectances? I see Kelvin gave us an answer, 0 to 1. I'm seeing 0 to 1. Okay, it's actually, again, a bit of a trick question. So EMIT reflectances can be less than 0 for the same reason that the radiances can be less than 0. If the true value is 0, we want to have noise about that point, right, that reflects the true noise statistics of the instrument. We don't want to truncate that noise distribution, or it will average out to something larger than 0 in the long run. So EMIT reflectance values can legally be less than 0, and that's intentional. They're also unbounded on the upper end, and the reason relates to our directional reflectance. So if we measure a glinting surface, we're going to get a value that's actually larger than 1. All that means is that the surface is reflecting less in some of those other directions that we aren't measuring, but the directional reflectance can legally be greater than 1. Okay. So these are what these surface reflectances look like. We see some examples of hematite absorption features, goethite. These are the kinds of minerals that EMIT measures. And of course, these are the fingerprints that are evident in the reflectance spectra. I've offset these reflectance spectra so we can plot them all in the same plot here. But you can imagine these are mostly values in the 0 to 1 range, but could be higher. Calcite and kaolinite are minerals that appear in the 2-micron region. And so this is the sort of thing that you can do. These are the mineral maps that you can make when you have reflectance available. Let's see. I have a little bit of time, so I'll talk about some of the other reflectances you can measure with EMIT. This is courtesy Nicholas Bond. You can measure snow grain size. This is a classic measurement, or ice grain size, by looking at the properties of snow. Here are some snow spectra from radiative transfer models calculated with different snow properties. So this is all evident in the directional reflectance spectrum. Looking at water properties, Rob alluded to this in his talk earlier as well. The water-leaving reflectance spectrum gives you information about the phytoplankton present in the water column, or the other water quality parameters like the amount of colored dissolved organic matter. This is shown in simulation, but you can actually fit these physical models to EMIT data in order to recover these parameters. And of course, natural ecosystems as well. Here are examples of vegetation spectra. As we increase the fraction of non-photosynthetic vegetation, dry or woody plant tissues, you can see this change in the spectrum, and also soil fraction. So these are distinctions that you can make with spectral data that the RGB image alone might not show you. Okay, so how do we produce this reflectance spectrum? I'll give you just a little bit of insight into how this is done. It involves an inverse problem. So we have radiative transfer models that, given the state of the surface and atmosphere, can simulate what the radiance at sensor would be. Here we're trying to solve the inverse problem. So taking that radiance that I just showed you with 285 different measurements across the spectrum, we want to solve for what the surface reflectance is in every channel, as well as a couple of additional parameters related to the state of the atmosphere, specifically the aerosol optical depth and the amount of water vapor in the atmosphere. So this is, right away, some of you will notice, an underdetermined problem. We have more unknowns than measurements that we're trying to use. So we have to bring some additional constraints to bear to make this problem tractable. The way EMIT does it is through a Bayesian inference. So we start with some initial guess about what the surface and atmosphere might be, and then look for the configuration of state variables that is most probable. So here's an example, a cartoon example of this, where you have the surface parameters on one axis and the atmosphere parameters on the other axis, and we twiddle them to increase the vertical, which is the probability of the state given the measurement that we measured. Here's an example of Bayesian decomposition of that. So we have the surface and atmosphere state that we're trying to infer, and this is proportional to the measurement given the surface and atmosphere state, and also a prior term on what the legal surface reflectances in this case might be. So we can bring some constraint to bear about that reflectances should be smooth across the near-infrared water features. We shouldn't have step discontinuities, that sort of thing. And this very weak constraint is enough to make the problem tractable and allow us to perform this inversion. Here's kind of the best visual example I've seen of this process. And this comes from a recent paper by Phil Broderick, and it shows exactly what happens in the EMIT science data system to give you those reflectance products. This is a wildfire smoke plume. So this is radiance in red, green, and blue on the left side. And we've decomposed that through this model inversion process into the radiance part of the physical system, and then the aerosol optical depth part of the physical system here. So we can, again, come up with a physical interpretation that is most likely to give rise to the measured radiance that we saw. And so this is what allows us to measure the invariant surface reflectance through variable atmospheric conditions. Okay, so let's take a look at the surface reflectance cube now, going back to the same image, but now looking at it in surface reflectance terms, just to see how that changes the picture and changes the interpretability of this image. Okay, here I am in Wiser, so I'm going to bring up our reflectance image, and you can see in my selection box here that it's almost the same file name as the radiance image, except that the product name, the product level and name is different. It's level 2A surface reflectance. So I'm going to click on that. And looking at the image, there's almost no change, right? But if I start clicking around, you'll immediately be able to see that things are different. So here's just a random patch of terrain. And you can see that there are some parts of the spectrum that are blanked out. These are water vapor absorption regions of the spectrum that are actually left blank because the atmosphere is opaque in those regions. We just can't see through the atmosphere there. So we don't try to estimate the surface reflectance in these channels. We just set them to a small negative value. But everything else is good legal data. And you can see already that there's some interesting absorption features in this particular area of soil. We've got what look like some iron absorption features similar to the goethite and hematite features that I showed you before in those spectra. We also have an interesting calcite feature or carbonate of some kind here at 2.3 microns. So this is another example of just how much information is present in a single pixel. We can tease it apart into all the component constituents. Let's look back at that pool of water. And you'll see here too, it's again, we're getting no signal in the infrared, but we do see a significant surface reflectance in the shorter wavelengths, and subtle divots in these water-leaving reflectance features can indicate things about the water column contents, the phytoplankton, etc. If I continue to click around this image, you'll see a variety of different spectral shapes. Here's some vegetation. This brown-looking region actually has quite a bit of photosynthetic vegetation in it, as you can see from the chlorophyll feature right here that I showed you before. There's our liquid water. This feature right here is probably those woody plant tissues again. So we've got some non-photosynthetic dry vegetation in this pixel, just like we do the photosynthetic. So immediately you can see that this data cube is just a huge font of information for us to mine, even from this single scene. You can delve into a single pixel and fit models for hours just trying to explain this single reflectance measurement. So it's really a fantastic data set, I think. I think you'll be pleased with the quality. We certainly were pleasantly surprised by EMIT's instrument performance, both in terms of SNR, but also spectral fidelity. And I think that manifests in the radiance and reflectance products too. But of course, we're always looking for feedback. And there are a lot of experts, spectroscopists here, who will spot errors and niggles in the data. And please let us know when you see those. Please send us some sort of note so that we can then fix it in the subsequent version of processing. All right, well, let's go back finally to the presentation, and I can close with just a short view, a short picture of where we stand today. And Rob previewed this in his talk, but I'll just quickly reprise. We have all the data already in the DAAC for these 2022 acquisitions that you see in blue. So this covers a large area of the EMIT target mask across Central Asia, North Africa, the Western continental United States. The acquisitions in yellow have already been acquired. So these are in the bank, but they're not yet delivered. They will be starting to be delivered over the course of the next week or so. So expect future deliveries to come. These should, over the course of the next few weeks, fill out in terms of the data that's available to download at the DAAC. And this includes both the radiance products that I've showed you and the reflectance products as well. So I have just a couple minutes if there are any questions. If not, I'll pass it back to Dana.
Thanks so much, David. We do have questions coming in our Q&A situation here. So let's see, a few ones that I'll highlight here. So I'm curious about the criteria used to pre-select target areas. It seems that some regions of mineralogical interest were not included. Could you expand on this? So maybe either you or Rob could expand on the selection process for the mask.
Yeah, I can say quickly, and then perhaps Rob can elaborate more authoritatively. But
Sure.
We did an initial selection process based on areas that the science team felt were likely to be dust forming. So this is based on historical satellite data, primarily looking at regions that emit mineral dust into the atmosphere. So it's not just areas that have minerals, it's really those areas that are forming mineral dust.
Yeah, that's exactly right. We use some of the frequency of occurrence of aerosols from MODIS, for example, to get evidence that these were regions where mineral dust was leaving the surface of the Earth and interacting with the Earth system. So there are hard rock mineral areas where they are not dust sources, and that's not the objective for which EMIT was proposed and must fulfill. But I will add that in an extended mission, which could begin later in 2023, there will be opportunities to adjust the mask over which EMIT is collecting data. So again, anywhere under the ISS orbit is potentially available for EMIT observations. And I know we'll be observing other regions, both ecosystem, coastal, and mineral in the future.
Great, thanks. And then there's another question. Where on the ISS is EMIT located, and for how long is the spot guaranteed? Dovetail on that.
Yeah, I'll let Rob answer that one too.
Yeah. So we're on ELC-1, and you can get a map of the ISS. I've shown pictures of its location that was taken from an astronaut looking across at EMIT, and we're looking down at the Earth. Right now, there is a plan to extend the EMIT mission into the future a number of years. The details of how that's being supported are still being discussed right now. So I would say I can't give you a concrete answer, but I think I'm very optimistic that these observations will be available as long as EMIT keeps working into the future.
Great, thanks. And then a question that quite a few people have is, does the EMIT reflectance process pipeline include BRDF, topographic, and/or shadow removal methods?
Yeah, it does not currently. So we distribute these directional reflectances. Let me bring that back up again. So the directional reflectance respects the BRDF of the surface. So whatever the BRDF happens to be, that's what you get in a directional reflectance measurement. We don't try to guess what the reflectance would be in some other viewing geometry, which is typically what the BRDF correction tries to do. However, it's up to the user if they want to apply those BRDF corrections. And this is something that we might look into for a future version of processing, but it's not part of our product currently. Topographic corrections are another thing. We have the capability to produce topography-aware surface reflectances. Right now, the reflectance that we produce is based on just a virtual surface that sort of aligns with the geoid. So you can imagine the reflectance is being of a pixel, which is roughly aligned with the Earth's surface, the spherical Earth surface. That could change in the future again. We have the capability of doing it. However, digital elevation models come with their own uncertainties to try and use topography in the atmospheric correction in a reasonable way can actually introduce more errors than it solves in certain circumstances. So we've currently left that also up to the user to apply their own topographic corrections or topography-aware atmospheric correction if they desire, using the DEM that they choose. And again, this might change in the future, but that's the decision that we've made currently.
Great. And just to be clear for folks that are asking questions, there are some questions that I think are going to be addressed in our next couple sections, so I'm not going to highlight them right now, but there is, let's see, there is another one here that I was just looking at. In the reflectance products, do you zero the water absorption bands or leave them as blanks or nans?
They're set to a small negative value. I think it's negative 0.01 in the deep water absorption features, and that's just to let you know that it's that they aren't to be used.
Great. And does EMIT also measure incoming solar irradiance needed to convert radiances to reflectance?
We do not. We use a solar model, actually the default ModTrans solar model, which is from Fontaine Law 2010, I believe. That's what we use. There's a bit of there's ongoing discussion about which is the best solar model. In my mind, it's sort of a moot point because our vicarious calibration strategies actually use that same solar model. So for the purposes of estimating surface reflectance, any errors sort of divide out, if that makes any sense. So we aren't too sensitive to minor variability or minor errors in the solar model. Where that would matter more is if you want to compare emit reflectances with the reflectances generated by some other instrument that uses different vicarious calibration approaches. Naturally, you can take the radiance that we measure and use whatever solar assumptions you want.
Great. And then there is a question that I'm not sure how much you addressed exactly, but what is the radiometric uncertainty of emit measurements?
Yeah, so you can think about radiometric uncertainty in two ways. There is a systematic error due to calibration error, and then there's sort of the pixel-to-pixel error based on the signal-to-noise of the instrument noise. With respect to signal-to-noise, we typically do about 400 or 500 times. So that means our signal is about 400 or 500 times greater than the noise throughout most of the Visnier and out into the shortwave infrared for typical observing geometry and reasonably bright targets. So the signal to noise is pretty good. The calibration error is probably about at the 3 to 5% level, I would guess, just based on the sort of the alignments and discrepancies that we've seen in our vicarious calibration experiments. It's not uniform, so some wavelengths are better than others, but that's about what I'd expect probably for users with emit data trying to compare those to surface reflectance measurements.
All right, great. Well, let's keep going. I am going to continue to monitor the questions that are coming in, and if they don't get answered in the course of the next couple sections, then we'll come back and be continuing to revisit the questions that are coming in. So,
great.
Thanks so much. So sorry, I think we're on to Eric now.
I'm not sure that we can hear you.
I just unmuted you. I got you.
Okay, thank you. Thank you, Dana. My name's Eric Bulch. I'm with the LP DAAC. That's the Land Process Distributed Active Archive Center. We're one of several discipline-specific data centers within the NASA Earth Observing Systems Data and Information Systems group. The LP DAAC is located in the USGS Earth Resources Observation and Science Center in Sioux Falls, South Dakota. And that's a lot of information. The main takeaway is basically we process, archive, and distribute land-focused Earth observation data. And you can visit our website at lpdac.usgs.gov. So now I'm going to walk through using Earth Data Search to find emit data. So when you get to Earth Data Search, paste the link in the chat, or can somebody else do that actually, in case anybody wants to look? So like the first thing we would want to do is go ahead and log in. You'll need an Earth Data login in order to download the data. And also you'll need that next week when we walk through using...
Eric, sorry to interrupt you here. Can you switch this way that you're sharing the screen? I think people are having trouble seeing it.
Yeah.
I'm sorry about that. There we go.
That's perfect. Thank you.
Okay. So the first thing you want to do is log in. Like I said, you can log in right here where it's got my name in the top right. And you will need a login to download the data or for our workshop session next week. So using Earth Data Search is pretty straightforward, but there are a lot of small underused features that can really improve your experience for accessing or downloading the data that you want, and also for collaborating. So like to find emit data, like first we can just search for emit. If we use quotes, it'll provide only exact matches. That way you don't have to deal with some other data sets that may have that in their description. Here you can see the 3 available collections for emit: the estimated surface reflectance and uncertainty and masks, the at-sensor calibrated radiance and geolocation data, and the corrected spacecraft attitude and ephemeris. So if you look at the collection right here, you can see that this data set is available in the Earth Data Cloud. That basically means you can use Amazon Web Services and use direct S3 access to get to this data instead of downloading it. Here for the collection, we've got an information or details button that you can click. And here, what that does is that provides you information like the DOI, a user guide, the LPDAAC dataset page, which if you take a look at the LPDAAC page for this product, you've got like a description, some characteristics, known issues, information about the product quality, and the various layers. But if we go back to Earth Data Search here, also there's some other things like your temporal extent, the format, different keywords, the mission sort of bounding rectangle for all the data sets collected, a general description, and then details for how to use the cloud access. These links here, this documentation explains how to utilize S3 to access this data. And then here, this link will get you credentials to sign in for that. So if we just click and go back to our search results here, another thing we can do just from this collection page is say we're interested in all the EMIT data here. We can just add this to our project. A project is sort of like a shopping cart for the data you're interested in. But if we go ahead and say, okay, well, let's download some surface reflectance data, click this, and then it'll show all the available granules. And a granule is sort of like a spatiotemporal segment of the collection. It's defined by like a position and a start and end date. Here right away, if we're just interested in downloading a single one, and we know which one it is, you can just click this download button. And here for this granule, there's 3 different files you can download. You can get the reflectance, the uncertainty, or the mask information. And here also, if we click on this, we can see the browse image to get a better look, sort of preview the region we're looking at. We go back. We can also add individual granules to our project or cart. Up here, you can look at the details for the granule, or you can filter it out and remove it totally. This view details option basically has all the metadata for the granule. It's got a start and end time. It's got an ID. It's got a polygon that bounds the region, and some other metadata that you can use to filter, including the cloud cover. And then you can get this metadata in different formats. So if we click back here and look back at our surface reflectance, we can start to filter these results. Over here on the left is sort of our toolbox for filtering. We can do like a spatial filter, we can add a polygon, a rectangle, point, a circle, or we can upload a file. And so if we want to upload a file, like the valid formats would be a shapefile zipped to include these components, like a KML, a GeoJSON, or a GeoRSS. But for today, I'm just going to draw a polygon. So you can just click and drag and move the map around. I'm going to say I'm interested in just looking for EMIT data in California. And so also here on the right, you can draw on the map with the tools. So I'm going to start to draw just a shape around California. And so we can see that that's automatically filtered down the number of granules all the way to 69. Say we want to edit what we've drawn. There are a couple options here. The little trash can will delete your drawing, or you can click the button above to edit it. Say we want to expand this a little bit into Arizona, we can make that change and then save it. And so that's sort of an overview of spatial filtering. There seems to be some kind of UI bug happening right now, but usually you can see where the granules are on this map. You can kind of see as I move the mouse that it's selecting something. And so this is sort of the track along which the ISS was collecting data. Anyway, also we can do like a temporal constraint. Let's say we're only interested in, let's see, August the 28th, for example, of 2022. We can just select that date as a start time and end time. And that'll further filter our results down. Another thing I mentioned before, you may have noticed, is that there are a lot of cloudy granules for this data since it's on the ISS. There's also a cloud cover filter. So we can filter, like say if we only want granules where there's less than 25% cloud cover, we can do that. Not a whole lot filtered out because it's California, but that did reduce it down to about 8. So now let's download this data. We can click the download all, or we can add it to our project. If we click download all, that'll bring us to this page, and it basically automatically adds it to our project. The project feature is pretty nice. Like you can just name a project and it will save it. And that way you can look at the granules that you've selected at a later date. And you can also share it with people if you want to collaborate on a project. So that looks good. So we click done here and we can click this download data. And that'll bring us to our download status page. Here we've got the 8 granules and we've got the 24 links, one for each of the 3 components, the reflectance, the uncertainty, and the masks. You can click these links to download them individually, or you can say this is a text file if you want to use something like wget to download them. Also here again, like you've got your list of S3 links where you can access the data via S3. And then also there's a nice tool here where you can basically download and run this script to download the data. It takes advantages of some command line stuff, and there's some instructions for how to set that up right here at the top. And then some additional documentation. And that's pretty much it for our data search. Are there any questions?
Let me take a look here. Well, there's some, let's see, okay, it sounds like this might have been answered already, but regarding searching for images, is there an option to select only or mostly cloudy or snowy scenes?
So there is, within the cloud filter, you can look at the cloud cover, but I don't think there's nothing to support like looking for snowier scenes.
Great. And is there a Python library for interacting with Earth data search?
There is one in development. I can't think of the name of it, but you can also use NASA. NASA has a CMR API that basically runs in the background, and that's what Earth data search uses. Let me see if I can get the link to that. But you can use that to basically do the same thing programmatically.
So this is kind of a question that's probably a multi-person answer, but what is the time lag between acquisition and data availability?
I'll speak to that a little bit, Dana. in some coming slides here.
Great.
Okay. Thanks.
And then is there a formal way to submit possible image errors or artifacts? And that's kind of, I guess, for a few people, but is that through the DAAC currently the primary way of doing that?
Yes, submit if you find any issues with the data, yeah, feel free to submit those questions or issues to our user services link. I'll post that in just a bit. Also, another great place for questions for identifying issues or reporting issues is that EMIT Slack channel that Dana posted earlier. Kind of become part of that community, and that eventually does make it back to the DAAC, and it's definitely hitting the science team early at that point then.
Great. And then just answering one other question that someone had earlier on, which was, were you expected to get information about the Python component earlier? No, we'll get to that probably in the next session. So, all right. Let's keep going then. And we do have quite a few kind of additional general questions coming up, so I think we'll probably have more time for question and answers at the end.
All right, is that over to me then?
Yep. Thanks.
Okay, great. Cool, and we will definitely have some more time because one of the items that I was planning to share here is actually going to get bumped till next week. So let me go ahead and share. Is everyone seeing the slideshow clearly here? Dana, can you give me a thumbs up? Great, okay. So I'm going to kind of walk through, nominally we were going to talk through data formats, but I'm actually going to, keeping an eye on the chat here as we went, actually going to talk a good bit about coverage and latency and expectations on when can you get data and when can you not get data, things like this, and then a couple other random topics. I don't think I introduced myself. My name is Phil Broderick. I work at JPL with David and Rob on the algorithmic development and data delivery for EMIT. All right, so the first thing to note about EMIT data is that while we are highly confident in our core algorithms and the data that we've been delivering to date, things are going to continue to evolve over time, right? We're actively learning about the system, and we are continuing to find improvements that can be made to the individual products. So everything that we are putting forward right now is the absolute best that we can figure out how to do it right now, but is also subject to change as we learn more throughout the mission lifecycle. And I'll talk a little bit about what that looks like in terms of delivery here. So, and I apologize, this is going to be a lot of wall of text in these slides, but that's we're trying to capture all of this information for you for the future. So EMIT data deliveries are going to work on a rolling cadence. So and this is all speaking to the first 1 year nominal mission lifecycle here. So at present, we've delivered about 5,000 scenes of the DAAC, and as you've seen so far, there are about 4,000 scenes that we have captured and downlinked and processed in our data center, but we have not yet uploaded to the DAAC. We are in the process of catching up with those deliveries, and once we do, then that latency will be reduced dramatically and we'll begin to deliver as we process data. Now, what does that latency actually look like? Sorry, I put two things there. The actual latency of the data is incredibly variable, and that's because we have a relatively limited capacity to download data from the ISS. Data actually has to get from the ISS, go to the HOSC in Alabama, the Huntsville Operations Center, and then get transmitted from there to JPL, get processed at JPL, and then get uploaded to the DAAC for everyone to use, right? So there's a lot of steps to get from A to B. That big bottleneck is getting down from the ISS the first time. So we're constantly transmitting these data down, but at a relatively limited rate, and EMIT gradually stores up data from when it acquires. So you can imagine that there's a rate that the data are occurring on a disk drive that's on the sensor, that's gradually building up, and it's gradually emptying at the same time. So it's kind of bursting full and then gradually emptying. And so when we are at a period in the mission life cycle where there hasn't been a lot of observations right beforehand, we can deliver things to users in a very low latency. So it can be as little as 1 day or 2 days. At other times, when, say, we've just captured 10 days of maximum solar geometry, excellent data, any individual acquisition, it's a first in, first out system. So it's going to take a couple days for that downlink to catch up and then get delivered. So I hope that makes kind of some sense. It's why there's going to be a lot of variation there, but in your head, once we get to a nominal delivery cadence, think 1 to 10 days-ish. It could be a little bit more. We're not actually required to deliver it for 3 months, but we know people want to see data right away, and so we're trying to do that as quickly as we can. Now, it's going to take us a little while to catch up to the delivery rate so far, catch up with IOC and the initial procedures. So think, David said a couple of weeks. We might get to a couple of weeks, but think by March or April, we should definitely be in this nominal cadence. And then the other important thing to talk about is, as I mentioned, that things are going to change a lot as the mission goes on. That's true. And so one thing to note is that there is a software build version metadata tag. That's how you can track what version of things are delivered. So any algorithm that we implement is going to be implemented as we make that improvement, typically error fixes, but any improvement we make will come into play, and then all of that data and forward will be processed with that new version. Once we hit the end of mission lifecycle in September, we will then go through and reprocess everything with the latest and greatest version, the best thing that we can do, and re-deliver all of those data. So if you go check that software delivery version, that will track which version of things you are using. All right. So this is that map again. The blue is what's been collected to date. The yellow, the blue is what's been delivered to date, and that you can go download now. The yellow is what we're catching up in terms of our delivery. And then just to give you a sense, here's that target mask again that we're starting to fill in. There are some locations that we've added as calibration targets or for various reasons that were not in the original target mask, which is why some of that coverage is just starting to fill in different regions. But this is the most current target mask that we have. And then the other thing okay, and so then in terms of the acquisition strategy, we've had a couple questions about that, like does EMIT collect data at a regular cadence? And the answer is anytime we overpass the target mask and we have a favorable solar geometry. So that means that we have a solar zenith that's less than 60 degrees. So the sun is reasonably high in the sky. We will collect data. Now, the caveat to that is that EMIT has an onboard cloud screener. So anytime that there are a lot of clouds, and we are very conservative with the onboard cloud screener, so there have to be a lot of very dense, very obvious clouds, we excise those from the downlink, and that's just to preserve and try to maximize the amount of the surface that we're transmitting back down. So with that exception, anytime we cover the target mask and have that good geometry, we collect an acquisition. Now, the ISS orbit is a little bit complicated, and it doesn't cover everywhere on the planet in a standard and nominal order. So, here's what that, before I get to the overall map, here's what that cloud mask might look like. So this is that onboard cloud screener, and you'll begin to see a lot of sections of data that have these kind of bands that go across them. Anytime you happen to see that in an acquisition, most likely, it can be from a couple different things, but most likely that means the onboard cloud screener identified that section as being very cloudy and excised it. And you can see that there are a lot of other clouds in this scene, right? Again, this algorithm is very conservative, so it's only taking it out when it's really confident that the majority of this area is quite cloudy. All right, so back to revisit rates here. So this is a simulated revisit rate over 1 year of mission, and this is with a slightly different target mask. So this isn't exact, but this will give everyone an idea of what the expected revisit number of revisits over the course of the year is. Now, the revisit interval is highly variable because it depends on the solar geometry, so it's going to shift. Sometimes you can actually see the same spot on the planet twice in the same day. That's happened several times already, and sometimes you'll see a lot of covers. So at the moment, we just went through a phase where we were seeing a lot of South America data coming in. Every other day, you were seeing this section of the planet come through. And then gradually that's shifting to the northern hemisphere, and it moves seasonally. And so over here, you can see that on the median, we're getting over 10 revisits per year, and that at the heavy tail, you might get some locations that get up to about 20 revisits per year. All right. Hopefully that answers some of those questions. And now I'm going to move on to everyone's favorite topic, data formats. I know this is going to be a little bit detailed and a little bit into the weeds, but the first thing that a lot of users want to do is get their hands on the data. So we want to try to talk through what our format actually looks like. So we deliver data in the NetCDF format. NetCDF is machine independent, it's hierarchical in nature. I'll talk about what hierarchical means in a data format in a second. And I know, again, many of you have probably used NetCDF data before. I'm just going to go into the detail for those of you who this might be a new topic for. The NetCDF format is self-describing, and that means that we label the data as variable names. So rather than include additional metadata, sometimes there's additional metadata, but in general, variables are actually labeled within the format itself, and I'll show you examples of that coming up. The format supports compression, and we do take advantage of that in several instances that I'll highlight. It also supports chunking if you want to use that, and sometimes you'll hear about an HDF5 format as well. It's important to note that NetCDF actually is an HDF5 file. It's a subset of that. And it's also an open standard format. Now, it's quite a bit different from an ENVI or a GeoTIFF or a COG or many other data formats that some folks might have seen before, in part because it's not an inherently geospatial data format. What that means is that while there is geospatial data embedded into it, not every viewer is going to know exactly where that data is, where those data are, or how to interpret them. And so we'll talk a little bit about what that looks like subsequently. The data themselves are also not provided in projected format, but all projection and gridding information is actually built into this file so that you can easily project that. And in the next week, we're going to show examples about how you can quickly reformat the data into your other favorite format and or project it very quickly on the fly. And then I'll just throw a quick shout out. There are native NetCDF viewers that exist. So here's one, Panoply, that's quite convenient. So if you download this from this link, you can open up and just take a quick look at what's in these files. A lot of the times this isn't the best way of interacting with our data, but it is a great way to be able to quickly see what's in the particular product that you're looking at. All right. So the files in the current deliveries data, David touched on this, but I'm just going to reiterate. So we have this L1B and L2A deliveries that have already come out. In that L1B, there are two different NetCDF files that are delivered. There's the radiance data and the observation data, and you can download both of those files independently. And then on the L2A side, there's the reflectance, and I apologize, I am missing the reflectance uncertainty here. That is a separate NetCDF file, so there are two NetCDF files there. And then there is also a mask file that's delivered in the L2A. And then each one of these files contains many data sets. All right, so how does a file contain multiple data sets? Well, it utilizes this hierarchical data format, which you can think of in your head like a file system. So this is basically a file system that's contained within a file. Our data have three main groups to them. There's the root or top level group. So these are features that are embedded directly into that top level. Then there's a subcategory. You can, again, think of it maybe as a folder of sensor band parameters. And so these contain information about band or wavelength specific information. And then there is a location folder, and that tells you where each and every pixel is located and how to project it onto the surface. There's also a whole bunch of metadata that is directly in the root system that's at that top level. And then there's two additional fields, and these are common to all NetCDFs. So these tell you the dimensions that all of the additional variables are going to be labeled as, and then the variables. And variables are where the actual data are stored. And I'll walk you through what's contained in those variables subsequently here. All right, so the L1B data, which is going to be approximately 1.8 gigs per tile, though it can vary larger. These are going to be our radiant scenes, and these are 1,280 lines long, 1,242 lines wide, wide being the cross-track dimension, long being the down-track dimension, and we deliver 285 wavelengths here in float 32 format. Now, a caveat to that 1280 number is that most scenes are 1280, but some scenes can be more. So when you start doing the data collection and you get to the very end, sometimes you have a little bit left over, so that we don't end up with instances where you have just a little bit of data hanging out at the end, which might induce some issues with some of our subsequent processing. We just concatenated that on. So every scene is going to have somewhere between 1280 and 2560 lines. And again, most scenes will have 1280 lines. All right, the location. So there are 5 different bands that are embedded into the location file. There's the latitude, the longitude, and the elevation of every individual pixel. And again, that matches the same 1280 plus or minus 1280 by 1242 and is also a float 32. And then you also have 2 additional variables that are provided that are the GLT-X and the GLT-Y. Now, GLT is a geolocation, geographic lookup table or geometric lookup table, which tells you the from a given projection that's also contained within this file and a given upper left coordinate where you would go in order to project each individual radiance pixel onto a projected coordinate screen. So it's basically a mechanism to very, very quickly orthorectify an image. And so those are embedded in this location folder. And this is true and going to be true for each and every one of the files that we deliver. There's also this sensor band names, and this is again where these wavelength specific properties live. So this is the radiance file. Now, I don't want to dive too deeply into this because this is going to be language specific, but say you were going to access data from this file, and Eric is going to walk us through a lot more of this next week, but you could imagine opening up one of these files from the DAAC. This is what the data format will look like when you download it. And then if you just open that up into Python using the NetCDF library, and you looked at DS and then the radiance, it would look like this. And then subsequently, again, because these latitude, longitude, elevation, and GLT files are underneath the location, it would basically be like traversing a dictionary and looking on down. And again, we'll get into much more about how to get into Python and interact with the data in the next 2 sessions. All right, moving forward to the L1B file. So these are the observation files. This is a much smaller file. It's about 100 megabytes, and these have 11 bands in them. You can find exactly what those bands are by looking at the sensor band names, and there's a property that's called the obs bands. And these are additional metadata that are typically used in the atmospheric correction procedure, but that some users might want to use. For example, David had some discussion about BRDF later and doing post hoc BRDF corrections. If you wanted to do that, some of the data that you might be looking for would be in this observation file. Include things like timing, sensor geometry, and solar geometry. Next, we have reflectance. Again, this is a 1.8 gigabyte file. Contains very similar things, very similar orientation to the radiance data. And David talked more about the reflectance product, so I'll set that aside here, but this basically matches the format very directly from the radiance file. And then lastly, we have the reflectance uncertainty. So again, very, very similar, except this time it has uncertainty. But last but not least, we also have a mask file that we deliver. Now, the mask file is a little bit of a catch-all. So in addition to having a mask, so it has a cloud mask, it has a water mask, actually has a spacecraft mask on it as well, just in case we happen to observe a little bit of the ISS incidentally, based on particular orientation of things. And then it has kind of an aggregate mask at the end. All of those masking parameters are here, but then we also capture the aerosol optical depth and the water vapor that are retrieved during the atmospheric correction, because sometimes those can be used as additional mask parameters for various downstream sciences as well. Because of those two, that 8-band file is delivered as a float 32. And there's also this additional band mask file. Now, this band mask is a wavelength by wavelength mask for each individual pixel. And it notes any time that during any of the radiance calibration procedure, for example, we might have noted saturation of a particular wavelength gets flagged here. It also notes any wavelength in a different way, notes any wavelength where any interpolation was done during the calibration procedure. So this provides a lot of detail, and users can take a look there. All right, I think that is mostly it for those files. I will highlight quickly that each one of these, some of those key band parameters that I mentioned, so for radiance, reflectance, and reflectance uncertainty, each one of those have the wavelengths as well as the full width half max at each one of those wavelengths listed under sensor band parameters. There's the observation bands that tell you which one of the bands are in, what the names of those bands are in the OBS file. There are the mask bands that, again, tell you what those bands are in the mask file. And then in reflectance, there is this good wavelengths. We had a question about that. So those are set to that negative 0.01 value, but they're also flagged within this good wavelengths band. Or in fact, it's the other way around. The good ones are identified in this band and the other ones are set to 0. Lastly, you'll find a couple other key parameters. So there's a geotransform. This is a GDAL style geotransform that notes kind of what the metadata about the spatial information of the pixel, as well as the spatial resolution. And we try to be exhaustive and give you as much information as we can. I'm not going to go. I think I just toggled in and out there, but I think I'm back. Okay, so there's the rest of the metadata fields. Quickly, there's lots of data to come soon. We've talked a lot about that. In subsequent weeks, we can talk about even further mechanisms for data access and ways of viewing data and things like this. There was a question about code, though, and where you might be able to find code. So I threw this in at the end. All of the mission code is available to everyone at our GitHub link that's here. And I'm sure we can throw that into the chat quickly. The atmospheric correction code is in a separate database, but this is the live mission code that's right here. I took this snapshot about 10 minutes before I started giving this presentation, and you can see that there is a variety of things that were updated just yesterday, right? Things that were updated last week. So this is live, actively developed code. If you think that you've found an issue with some of our processing, or have a suggestion, or that you want to submit as a pull request, please feel free. Issues and PRs are welcome all the time. And with that, I think we have a little bit more time for questions or things that I might not have gotten to here.
Great, thanks. Yeah, we will move to some questions, and I'm trying to kind of group them. And you just answered one of them, which was, is the reflectance processing pipeline code open source?
It is. So there's both the full repository that was that ISOFIT link that I put up there that has the full procedure for that atmospheric correction, including all of the radiative transfer modeling, which is also open source in this context via an emulator. Now that code is implemented in a specific way within our science data system, but the full science data system is also open source. So if you go under that EMIT SDS overall organization, you'll find an EMIT main repository, and inside of there you can find the exact calls that are made on our science data system. So not only the full repository, but the very specific calls that we're making actively. And if you have further questions on details about that, you can always submit them to us.
Great. There's also a question about, do scene geotransforms use rotation?
No, they do not. So we are north up in our, or I suppose technically they still do, but the rotation is 0. So everything is north up.
Great. And then there's a couple questions that are kind of along these lines, but how can one determine the temporal resolution for a site and plan future passovers for field validation? And then there was another question very similar about is it possible to know where acquisitions will be coming in the future?
I can take a shot at that here, and then others can chime in. We have some knowledge very far into the future about where things are going to be, but the accuracy of the forecast of the ISS coverage degrades quite rapidly over time. So as such, our most confident predictions about where we're going to cover basically roll in on a weekly basis. So every week we get a 2-week forecast of where we think we are going to cover data in the future. We don't have it quite ready for it today. I was hoping to be able to show you, but next week, if you come back and tune in, we will show you a tool that, in addition to showing you the current coverage and linking to data from the DAAC, will actually show you the forecasted coverage for that 2 weeks, and that will be very actively updated. So every Wednesday, you will get a forecast for the next 2 weeks. I know many people that do field work would love to know farther in advance than 2 weeks, but I think that we'll talk about ways that you can use that forecast tool and get a sense of when coverage might be coming to your location. And then you can see the exact anticipated tracks in advance of when they actually come.
Great. Somebody says maybe this is obvious, but I'd like to clarify anyway. Is all the EMIT data hosted by AWS free?
Yes. I will let one of my DAAC colleagues. Yeah, great.
Yes, the data is available at no cost for download and access. If you are, we haven't mentioned this too much, and we won't show this next week, but future, hopefully, webinars will. When you access the data directly in the S3, you have to be in a specific AWS region, specifically US West 2. But otherwise, data downloaded from like Earth Data Search is completely free to our users. Yep.
And this may be another question for you guys. Will the customization option in Earth Data Search eventually be enabled for EMIT data? I'm not sure.
As the mission, as we go forward, we'll evaluate what services we can apply to these data. So I can't really give you a hard answer right now. We're still kind of in an evaluation phase for those types of services out of Earth Data Search.
Great.
But we do have a number of resources that we will highlight next week, and we continue to kind of add to that will kind of make it easier to work with these data, because they do come in somewhat of a difficult initial format to work, not format, but structure to work with, much like many of the data products that come off of the ISS.
Great. And one of kind of a follow-on question there, can ENVI read this data format, or do we have to go through Python? It's kind of teeing us up next week.
Yeah, I think we'll push that question next week. So the answer depends a little bit about which version of ENVI you happen to be using. But some versions of ENVI, the more advanced versions, can read this as long as you have an associated XML file that we can provide for you. And then actually future releases of ENVI, we hear will have a native EMIT viewer. So it'll just be baked into the software package. I don't quite think that has been released yet, but it will be coming down the line. And then similarly, QGIS, the QGIS team is actually working on a plugin as well, so that, sorry, not the QGIS team, the EditMap Box team, which is a plugin for QGIS, is working on a advancement to their plugin so that you'll be able to directly natively read EMIT formats there.
And I do have a slight modification to that, Phil. You can use the GLT files that are inside the NetCDF file to actually get a georeferenced image out of ENVI 5. plus. Yes, you got to use the newer version of that, but there is a slightly manual way of getting that data correctly orientated and georeferenced in ENVI. So yep, there is a way.
Great. And then this one's kind of a two-part question. I'm actually going to start with the second half first, which how big is each file at level 1 and level 2?
It varies depending on the exact file, but the radiance, reflectance, and reflectance uncertainty are each approximately 1.8 gigabytes. The mask file is approximately, let me go back, I believe 50 gigabytes, and the mask file involves a decent amount of compression. So it depends on the exact file, and then the observation file is about 100 megabytes.
Great. And the kind of first part of that was actually a question about running Wiser and suggested computer memory and CPU that would make it easy to do that exploration. We aren't developers of Wiser, so we may have to dig into that and find out, unless you guys know offhand.
I would have to look at the question in more detail now. Sorry.
Okay. All right. Are all target areas being observed in multiple seasons?
That's a little bit of a complicated one. So again, we cover whenever the ISS happens to overpass a particular site. So some locations will see coverage and when there's favorable solar geometry. So some locations will see very frequent revisit rates. Most places most places that are within the target mask will see an observation in multiple seasons for their particular latitude or longitude. And most places, again, the median are going to see a little bit over 10 revisits over the course of the year. Some of those are going to be probably pretty clustered. So you'll probably get those in chunks, maybe at 4 times over the course of the year. But again, it's very specific on the latitude and longitude.
Great. And then there's a couple different questions about, well, there's what is the average pixel size for EMIT pixels?
It's about 60 meters, not exactly 60 meters, but it's approximately 60 meters at the equator.
Is data removed by the cloud screening process permanently lost?
Yes. So we observe it, and then before we downlink it, it's excised. So those cloud cover data from that cloud screening process are never downlinked. So we never see them on the ground. Now, on the ground, we perform a more advanced cloud screening algorithm, and that's what comes with our mask. So those data are not lost. And again, this is why we make that cloud screening algorithm so conservative, is so that we make sure that we're quite confident that these scenes are very, very cloudy. Now, I will say, for those folks that might be interested in cloud science, there are still plenty of clouds and even plenty of dense cloud decks that don't make it through our cloud screener because of how conservative it is. And in fact, we've used those in calibration procedures to date. So you can still find plenty of clouds if that is your domain of interest.
And an associated question on the cloud masking is it reasonable to think that some areas with heavy smoke or dust may also be masked out?
The cloud mask should do a fairly decent job of discriminating between high AOD levels, but there is, in addition, the aerosol optical depth that comes into play. And I would suggest that, so one of our screening parameters for the prime mission for identifying mineralogy is to exclude areas that have an AOD, I believe it's above 0.5. Now, different users for different activities may think that that is too conservative or too loose of a threshold. And so that's why we provide those AOD values that are retrieved from the atmospheric correction process so that you can easily threshold and apply your own mask to the data.
Great. Let's see. A couple kind of more instrument type questions. Is the EMIT sensor co-aligned Wiener SWIR sensors, or does everything travel through the same optic path?
There is one focal plane array for EMIT. So there's one focal plane and one optical system. It's in fact a very, very simple design. So light travels through one pathway and hits one mercury cadmium telluride detector.
Great. And does EMIT have an onboard calibration system, dark radiometric spectral?
I'm just answering these because I believe David's not online. Is that correct?
Yes, yeah, David hopped off.
Great.
So yeah, so you're
Okay,
on you're on the hot seat.
Great, no problem. No, EMIT does not have an onboard calibration mechanism. Instead, EMIT actually uses observations on the dark side of the orbit in order to calibrate. And we've been able to demonstrate by successive, and these are areas that are when the solar geometry is very low, so they're on the dark portion of the orbit, and then they're also over water, so that there's basically no radiance that bases back to the sensor, and we've been able to show that those vary on the order of only 1 dN on a standard deviation, which is very, very low. So we're quite confident in that as a dark target calibration strategy. Then David mentioned this a little bit, but for the rest of the calibration procedure, we utilize vicarious calibration targets. So David has a methodology worked out whereby cross-track variation, for example, in the depth of the oxygen A-band retrieval can be utilized to characterize things like spectral uniformity. And there are other atmospheric features that can be used in a similar way. Then we also use a series of vicarious calibration targets across the ground that we coordinate with some USGS colleagues and some field teams in order to additionally fine-tune that calibration procedure.
Great. Is EMIT pointing straight down, or does it have a tilt?
So we're actually subject to how the ISS happens to be flying. So it can actually vary. And in fact, the instrument can fly in reverse sometimes. This does happen occasionally. So it varies. Typically, we're seeing something, if memory serves, so don't quote me here, but I believe we're seeing something about 11 degrees off nadir, but pretty close to nadir in general. That information is captured for every individual scene in the observation file.
So then there's a couple of questions kind of around the mask and the extent of the mask and outside collection. So I'll kind of ask a couple and then maybe we could just elaborate at one time. But is the EMIT mission open for satellite tasking to cover an AOI site not currently covered? Is it possible to get raw image data from outside the EMIT mask areas? Let's start with those two.
So yeah, again, I'm just taking a look and I don't see Rob, so I'm just going to keep answering questions. So the during the prime mission, the EMIT target mask is fixed and designated by the EMIT science team in order to achieve that overall objective of constraining the sign of radiative forcing. So we're not doing tasking at the moment. I believe in the context of an extended mission, that would be a different story, but I am certainly not an authority on that. So we'll have to wait to hear what happens there. There was another question that was embedded there. Oh, can you see raw data from outside of the target mask? It's a good question. So anytime, right, the sensor doesn't turn off per se, it observes everywhere that it actually observes, but we never actually record those data that are outside of the target mask. So we only actually record it to the solid state recorder when it's within the target mask, so it's impossible to recover anywhere else.
And I think that basically answers this another question, which is it possible for the EMIT sensor to collect data continuously so that the L1B top of atmosphere radiance can be archived? So that answers that question too, I think.
Yeah, and all of these choices are fundamentally a downlink constraint. So as compared to some other spectrometers that are on orbit or have been on the ISS before, EMIT has a much wider swath. So the areas that are covered, we cover 60 by 1280. I should know these numbers off the top of my head. About 75 kilometers in a cross-track scene. So it's an incredibly wide area, and because of that, and because of the downlink rate that we have from the ISS, we can't possibly downlink at all.
Great. And one more kind of mask-related question here. How are the non-semi-arid target areas defined?
So there's a sequence of areas that you might have seen kind of in scattered red dots through the scene. Those are those are calibration targets. Generally speaking, those are things like AeroNet sites that we can use to calibrate our reflectance data. Although, for example, a whole sequence of neon sites have also been added due to the capacity to use coincident measurements from those neon AOP sensors for additional vicarious calibration. So there's various targets that are in like that. Then there's kind of the adjacent lands concept. So part of the EMIT mission is not just looking at what the sign of rate or what the contributions of emitted dust are on rated forcing now, but also into the future. And as such, the mission is interested in figuring out what the mineralogy is of areas that are immediately adjacent to arid regions that might not be emitting large quantities of aerosols now, but could possibly in various future scenarios. And so you can think of it as a buffer around current arid regions that kind of expands potential regions. So things, south of the Sahara, there's a decent collection and regions that are in those kind of surrounding buffer regions.
And let's see, another around kind of downlink and latency. Is it possible to prioritize certain imagery for lowest latency download, specifically imagery of the US or other locations?
At the moment, no. So the operation is proceeding as first in, first out.
Let's see. Does the calibration account for adjacency effects?
So I'm going to interpret that question as asking, different people have different nomenclature here, as asking actually about the surface reflectance and not about the calibration. If that was not the case, please just restate that you're very specifically interested in the radiance calibration. But people often talk about adjacency in the reflectance, and at present, the adjacency, so the contribution of photons via multiple scattering back to the sensor, is not accounted for in the reflectance procedure that's used right now. There is a little bit of a extended conversation about how the atmosphere is retrieved, and currently the strategy that's deployed based on some work by Regina Eckert can be shown to be equivalent to solving all atmospheric states simultaneously within a scene. So there's a little bit of coupling that's going on there, but it's not an adjacency effect from the surface, which is, I believe, what the question is focused on.
What is the possibility of EMIT data in quantifying or assessing variation in soil properties, soil organic carbon, soil nutrients, in agricultural fields?
I've been talking a lot. Dana, would you like to answer that one?
Sure, I would be happy to answer that one. Yeah, I mean, I think that's a very interesting potential application of EMIT data, and there are a couple folks on the EMIT science team that are very interested in looking at soil properties in agricultural fields and other places. So I would say that is an area of active research that I think there's a lot of interest in. All right, we're getting there. Is there a seasonal pattern to dust transport globally? Does restricting collection times to when the solar zenith angle is less than 60 degrees constrain the sensor's ability to retrieve important dust events?
So there's an important clarification that should be made here, which is that the objective of EMIT is not actually to observe the dust events themselves, but rather to observe the surface mineralogy in dust emitting regions. So the reason is that Earth system models are going to be used to estimate what emissions would look like in various schemes, and importantly, how those emission scenarios might evolve through time, especially as things like vegetation cover changes over the surface. So our goal is not actually to find those dust events and measure them themselves, particularly because they're so sparse in nature, right? It would be like looking for needles in a haystack. Even though there are quite a few dust events, you'd kind of have to be everywhere all at once at just the right time of the year, and that would be very hard to anticipate, which is, I think, what the question is after here. So, so we're after that surface mineralogy, and we can cover everywhere within our target mask, even between that 0 and 60 degrees zenith angle, quite comfortably.
Great. And then this is the last question that I have here, I think. How can one determine the temp? And so this is kind of a bit of a revisit, but how can one determine the temporal resolution for a site and plan future passovers for field validation accordingly? And I think that's something we're going to get to talking a little bit about next week. But Phil, if you don't mind just kind of reiterating your comment around that, that would be helpful.
Yeah, and maybe I'll go ahead and I'll bring this back up here. Just quickly share this screen. So again, it's highly variable over the planet, and what I'm going to draw your eye to here is these areas in North Africa. Just because of the forecasted ISS trajectory, it's actually quite hard to estimate what it's going to be in a particular location, because the prediction drifts from the actual measurement by a decent amount in the cross-track direction. Even on the 2-week time scale, where we have a pretty good understanding of where we're going to be, we can be off by about 15 kilometers in the cross-track direction. So it's not perfectly precise. Now, that said, we can get a general sense of where are more likely and less likely to have more revisits. So if you happen to be lucky enough to be very interested in a site that's at the tip of South America, you're going to get a lot of revisits, particularly when data are when the sun is in the highest in the southern geometry. We will provide in this same tool, as you can see up here, in the same way that you're going to be able to see where current acquisitions have come. You will be able to see a 2-week planning forecast coming into the future. And we can talk a little bit more next week when we have that tool in front of us about how you can strategize for coming field work using that. The other thing that I will say is that we have discussed various formats for notifying people when their locations might be covered, and we can pick that up as an action item for more detail in the coming weeks, since there seems to be a good amount of interest in this topic.
Great. And we do have a question here. How's calibration performance in EMIT? How has calibration performance in EMIT been so far? Can you comment on the performance of the near UV channels, 380 to 420 nanometers?
Yeah, so that's an excellent question, and I wish David were here, as he is certainly the authoritative figure on this. But I will say that so far the performance is exceptional. We are very, very pleased, not only at the signal to noise level, which tends to be quite high in the many hundreds, and can get exceptionally high, can get up into the 750 range quite comfortably in the near IR channels, depending on the surface target, of course. But in addition to the really high SNR that we're seeing, the spectral uniformity is really quite good. So David is working on a manuscript now that should come out shortly that will characterize that in full. But I believe that he is well within 2 nanometers in terms of spectral uniformity, and more like 1.5 nanometers in terms of spectral uniformity peak to edge. And I'm getting my units totally wrong there, 0.15 nanometers peak to edge. So it's really quite good. And we've been pleased with the results so far. Of course, atmospheric correction is a challenge when we're talking about global scenes, particularly when we're talking about locations like in South America here that might have variation in elevation that might exceed 7 kilometers in a particular scene, which is extraordinary, or certainly 5 kilometers on a regular basis. And so atmospheric correction is always a challenge being applied globally, and we're working at getting that better all the time. We've learned a lot about over the course of the mission so far, but I would say that so far we're quite pleased with those results as well, and we'll be interested to hear additional user feedback. But so far we're quite happy with what we see.
Great, and then I think this one might be for you, Eric. Can we easily find data that are co-located with other sensors, like Ceres?
I'm not sure that I have a great answer for that. Aaron, do you have an idea about that?
So you can definitely use Earth Data Search and CMR API to, add temporal and spatial constraints to search for those data. I don't think any of the sensors on board the ISS are completely kind of one-to-one with regards to how the sensors are lined up. So yes, you can identify where observations are taking place based on spatial and temporal constraints that you can submit through Earth Data Search or through the CMR API.
Great.
We have made some attempts to coordinate with some other missions. For example, I believe we've provided our target mask to the EcoStress team, and so far as I understand it, the EcoStress ranking is not quite the same as EMIT's, but I believe that it is somewhere in the ranking deck for determining whether a particular scene is acquired. Again, not an expert in that domain, but I believe that they're using that as one of their criteria.
Great. Okay. Oh, not sure if someone already asked this, but what atmospheric correction algorithm is being applied to the images?
So we're using an open source implementation of optimal estimation that's implemented via the ISOFIT correction procedure. And there are some specifics to the particular algorithm and processing flow that's being done here that I might defer to a later conversation and or refer you to a manuscript because that's a bit of an extended conversation, but it's optimal estimation via ISOFIT is the short version.
And we did put a link to the ISOFIT repository in the chat previously as well. And I think a lot of these resources are available, and information is available on the EMIT website as well, and we're continuing to update that. And we, I think, both on the EMIT side and on the DAAC side are probably going to take a lot of these questions and continue to refine the types of information that we're providing to the community based on what you guys have asked here. Okay. How quickly and where can we find the recordings of these workshops? All right, that's for me. So we are going to do our best to get these up. We will have to go through some internal approval processes. So I will do my best, and hopefully we will have news for you on that front by next week. We'll also be doing our best to put up the slides that people used to share those as well. So we'll get that going once we're done here. All right. Well, I think we're kind of at the end of our content here, and so I think people are usually happy to have a couple minutes back to have a break between this and going to lunch, for those of you on the West Coast anyway. So thank you so much for joining us. We are hoping to see many, if not all of you, again next week to kind of dig a little bit more into the data. And is there anything from, Eric or Aaron, that you want to say about data access for next time for folks at this point?
Sure. So next week, we'll be using a cloud instance to work through a Python notebook for reading and emit data, plotting it, and doing a little bit more work with it. And in the registration, we ask everybody to provide their GitHub handle. That's how we're providing access to the cloud instance. So if you can send us that information, if you didn't put it in the registration, or if you're really interested in following along, we plan to show up about 30 minutes early so people can get on the cloud instance if they'd like and play around with it a little bit. Is there anything else from you, Aaron?
No, that GitHub handle will be crucial if you want to follow along. Again, data's free. This platform we're using will be free as well. It just requires a GitHub username to get onto it. We'll be working from some resources that are currently available to the public. I'm putting that link in the chat. It will be a version of that, or it will be a separate branch of that GitHub repository that we'll be working from. But if you want to get a head start, all those materials, or at least the majority of those materials in there, can be worked on from your local machine if you have that Python environment set up. And so feel free to go ahead and come with questions or just follow along while we do it next week.
Wonderful. All right. Well, thank you so much, everyone. And I look forward to seeing many of you again next week.
Thank you so much, everyone.
Thanks, everyone. Thanks for the great questions.
Thanks.